And we're live from New York. It's not Sabado noches. Okay, good. Well, very good. Welcome. I hope you had a terrific weekend. And for us Lubbock folks, we didn't inhale too much dust on Saturday and inhale too much unhealthy beverages and lipids and salts yesterday while parking our butts in front of a television set. It looks like there's some grins there, so either you did it or at least didn't know what yesterday was. I'm going to share my screen in a second. Today's lesson on Blackboard is called Lesson 5, but today's really a workshop. So the agenda for today will be to do some of the computations that you might normally have to do and see how to try to automate elements of the process, as well as give us a feel for what's going on under the hood of something like SWM. And then we'll do some swimming too. Okay, so with that brilliant lead in, why is it that my allergies kick in as soon as I'm doing a class? I must be allergic to work. They don't have a pill for that. Okay, screen sharing. To share the screen, I have to click on that. Okay, so you should see my desktop. All of our lovely faces are off here to the right. I'm going to push them a little bit further to the right so they don't get in the way. And a typical Blackboard entry, and I'll just go through the DO1 entry. I just verified a few minutes ago that the Lesson 5 link is working for both Blackboard entries, so you should be good to go. So what we're really going to do is we're going to go through the calculations of normal flow using the JupyterLab application, and then we'll repeat it in SWM, and then time permitting. So I don't know quite how long this will take because I intend to go slow enough for you to see what I'm doing rather than the usual move stuff around as fast as possible and make pretty pictures. And if there's sufficient time, we'll move on to gradually varied flow using JupyterLab and variable spatial steps. So at some points in your past career here at Texas Tech or wherever you were before, you've done these. But in all likelihood, in some likelihood, you've never thought about how to automate them to the point if you had to do repeated computations a lot. And so that's what the focus of today is. So taking the Lesson 5 link, no brains are required at this point. So the only thing here that would be readable for you on a web browser is the HTML file, and I've left some notebooks behind for myself. But let's start here with what I'm calling a computational workshop. So this is a series, perhaps this is our first workshop in a series, but we're going to look at uniform flow and gradually varied flow today. So recall from last time, uniform flow is the case where friction slope or the slope of the energy grade line in a channel is the same as some representative topographic slope, S sub 0 in this case. And gradually varied flow extends that by adding the water surface depth taper, this dz dx term, and a convective acceleration term. So changes in the speed of flow as a consequence of geometric changes and gravitational pull downhill. And then dynamic flow has got even more letters of the alphabet. So the objectives today are to explore the JupyterLab environment and make some relevant computations, and then compare the results to SWM. So we'll start with a steady, uniform, or normal flow. And you know it's normal flow because if it wasn't, it would be called abnormal flow. A uniform flow is a situation where the friction slope and channel slope are the same. And in such a regime, the profile grade line, channel bottom, and the hydraulic grade line, the water surface, and the energy grade line are all parallel. That observation leads us to be able to state that friction slope, the slope of the hydraulic grade line, or the water surface slope, and the bottom slope are all equal in this particular flow regime. With that in mind, we can pick a head loss model to describe how to relate losses in the system. Could use Darcy-Weisbach for non-circular conduits and some kind of correlation for the friction factor. Or the more commonly used is Chezy-Manning. And I've rewritten Manning's equation in a head loss format. It's not often written like this, but it's just simply a rearrangement of Manning's equation. Now, the typical calculations that we'd be concerned with in a design or an assessment setting are trying to figure out what the flow depth for a given geometry is for a given discharge. And that discharge might come from a hydrologic response model that's somehow integrated into the process. That's a different way of thinking about it than we presented in other courses. The computation of flow, given the slope of the water surface, is actually quite trivial if you know the geometry. But if the discharge is specified and you know what the geometry is, figuring out how deep it is in a particular geometry is a little, it's not intellectually any harder. It's a type of calculation we don't do routinely. But keeping that in mind as a structure, we're going to build some simple examples and then try to build, I'm using a new buzzword du jour, an extensible model tool. That's a fancy word for saying if we can make it work for one thing, we can make it work for many. That'll predict flow depth, and I'm going to choose rectangular channels, frankly, because the geometry is quite simple to manage. And we will compute node depths at ends of each section of a channel. Then we'll connect it together and look at what there is to see. I'm literally going to do just 2 sections, and I've intentionally written the scripts in such a way that would in some sense be dumb, but not if we're looking at 2 sections. So I'm going to sketch those 2 sections right now, but let me switch to my overhead camera. So up in the right-hand side, you get to see. And the reason I'm drawing the sketch is I'm about to invent some variables, so I guess you need to know what they are. Let me use the correct notation. 0, 1, and 2. Oh, use the color. And I know I'm drawing and you can't see it yet. That's H. Okay, here's what you guys got to all stand on your head. Let's see if I can fix that. That's a little better. At least it's right side up now. So here is a channel, and it's going to be rectangular with some width, and some flow depth. And I've shown 3 locations, location 0, 1, and 2. And the reason I'm starting with location 0 is the scripting language for this class. That's how it starts counting. And at location 0, there's some known elevation at the bottom of the channel. There is the known geometry, and we're going to try to compute and essentially draw this water surface. So one of the challenges, I'm actually trying to take a simple problem and describe it to a computer, and usually that is very hard to do. Computers are really good at complicated stuff that nobody can check them on, but simple stuff that human beings do without really putting much mental effort into it baffle the crap out of computers. So here's our typical calculations. We're going to try to do that modeling thing, but first we have to build a few things. So I've listed some functions here, and to make it a proper workshop, I'm actually going to go and get to my JupyterLab environment. And I believe last time I established that I can cut and paste wantonly. So keeping that in mind, I will do that. The first thing, I don't want to work directly on the class server, so I've already set that up, and you see I've got about 1 hour worth of clock time available. That should be plenty unless I do something stupid. So I'm now connecting to my Windows machine, and the reason I selected that instead of using it on the host computer is I want the ability to go do SWM after we mess around with the JupyterLab environment. Guess I'll do that. So if you're choosing to follow along, I'll try to go slowly. I think I will be forced to go slowly by virtue of the network lag. So now I'm waiting for my thing to load. See, I'll leave that open in case I actually have to do management. And as I recall, remember that the mouse response is painfully slow. Oh, and it's not going to let me get to what I want because, no, I don't want to install it. I actually want to run something. I want to run this guy. Install. Oh, that's weird. Maybe that's why it hasn't been working right all along. Hopefully that is the correct button to press. All right, we're looking good so far. And I already know not to attempt to change the defaults because all it does is go slow. It should play the song that's done during Final Jeopardy. Okay, excellent. So here is, today we're going to create a new Python notebook. We're going to call it, I'm going to call it Workshop 5 to be consistent with the lesson number. And what I'm first going to do is I'll copy and paste these various functions over. But let's go look at the functions. I believe we hit these last time. So first is a depth area function. And the syntax of Jupyter notebooks is these are essentially Python scripting instructions. The keyword define means def is to define a function, and the normal syntax is the name of the function, any name you want, the positional argument list. Positional meaning whatever the first thing is will appear wherever depth occurs in the function, and whatever the second thing is, in this case width, will appear wherever width is in the function, and then the colon. And that establishes a structure, and then after the colon, you can write your various mathematical instructions. This indentation is important. The Python and the Jupyter Hub and similar scripting languages use indentation as scope delimiters. You're probably familiar with scope delimiters in R. They use a curly bracket. Fortran simply uses parentheses. MATLAB, I think, uses square brackets. And this language, just to be different, as form of job security for people that are undisciplined, uses indentation. If this is a first time for you, that's going to really bother you. After a while, you get used to it, and after a longer while, you kind of like, yeah, that's not so bad. They whoever thought that up had some insight. So here we have a function called area, another one called perimeter, another one called radius, another one called slope 0, because I have no creativity in naming things, and a function called qnorm, which is essentially Manning's equation in SI units. And you know it's in SI units because of the constant in the numerator. I'm simply going to copy these and paste them here. No, that's not it. I just uttered a bad word. Okay, that's not what I want to have happen. Plan B. Let me go ahead and get this URL, and I'll just go here. Let me see. New tab again. What part of paste didn't you understand? $54,243. That stuff, when it works great, is wonderful. When it doesn't work great, makes you want to seek out. I guess we'll pick on Jeff Bezos. He's still CEO. 252. 9. Okay, here we go. Now it's on the, everything's happening on the remote machine, so it should not protest cut and paste. But being a Windows product, we get to see what the inside of a black hole looks like. It's dark. I guess that's why light can't escape. Oh, brother. Yeah, cloud computing isn't going to really do good for a few years yet. Okay, plan B. I am going to exit this and I'm going to do it locally on my host computer, because I simply do not have the patience to wait for the Windows operating system to actually function. Okay, I think I click on this thing to disconnect. Ta-ta. All right, let's go back to running it locally. We will wait for the local Windows system to come to life. And it too is, oh, I wonder where in the world that is. It's a real pretty picture. All right, here's our local version, and I'll go ahead and hopefully I do have it already installed. Okay, so I click on that and wait. Oh, now Microsoft Teams has to request some passwords. See if I can ignore that. Yeah. All right, here we are after 10 or 15 minutes of fussing around, but that gives you all time to catch up anyway. I planned that. Yeah, that's it. I'm going with that. It's a pity they don't have the button where you can actually tell it what you really think. Okay, so don't think I want today's examples. I probably want to make a new folder. Okay. Workshop 5, one more time. Bet you I get it right this time. I hope. Okay, I need that to stay alive. This was what I was trying to copy. Hit copy, hit paste. Okay, I can live with that. That's not perfect, but that will accomplish our task for today. So we'll create a depth area function. And how do we test the function? We simply type its name and put 1 foot deep, 5 feet wide. The result should be a 5. And if I use this little symbol here, which will run the selected cell, or I can press Shift Enter. All this documentation is online somewhere. So there's our first function. Let me get the wetted perimeter. And I'm pretty sure that these functions actually work, so I'm not going to test them for the remainder of this demonstration. So all I'm doing right now is, now copy pasting is not a terribly important skill for you as an engineer, but it's easier than typing. So when a copy paste will do the job, by all means don't be ashamed to use it. And we'll tidy things up. That's probably mostly for me because I get offended when things look sloppy. Okay, so what I've just done, whether you know it or not, is I actually have just run those cells and nothing happened, except that these little numbers in the square brackets changed, and it didn't produce a pink block of error messages. A lot of times it will produce pink blocks because of error messages. Don't take that as a value judgment. Usually, why did it do that? Oh, that's right, because I'm in a virtual machine. I want to make the navigator get small. That's better. Don't take it as a value judgment. Usually the error messages are actually useful. I have to say this is one of the few environments where the error message is useful. Unlike dealing with Wells Fargo Bank software, the error message isn't very useful. It just simply says there's been an error. We're going to put everything to 0 and you get to start over, which is kind of hard. And so now let's proceed with our original goal, which is, well, suppose that we have a given value of discharge, and we know the geometry. What would the flow depth be according to this steady flow equation? So one way we would proceed is, let's go ahead and specify some values. So I'll add that to another cell, and I'm going to create an object named width. I'm going to give it a value of 5 meters, 5 feet. Well, actually, that has to be in meters, so 5 meters. I'm going to have a object named Q design. Think of that as design flow, 10 cubic meters per second. A value for Manning's N, but this is a good German man, so Manning of 0.02, and then an elevation of position 1 of 100, a corresponding to location 0, and position 2 of 99 corresponding to location 100. So if we were going to draw those things, which I will do right now. Well, maybe I'll do it right now. There we go. Here's our x-axis going that way, and we have a location 0, that's x1, of a location of 100 units, 100 meters, if you will, x2. And we have a vertical axis. I'll call it y for now. If it was subscripted with 0, then it could go y. Why not? And so we have z1 is 100, and z2 is 99. So pretty much we have a change of 1 unit in 100 units of distance. So the slope of this thing is equal to dimensionless 0.01, but we'll never actually need to bother with that directly. That's why we made these functions, to do all the work for us. So if we were doing a one-of calculation, there'd be no point in doing this. That would it would border on stupidity, almost making over the edge to insanity. Because you could do this with a hand calculator quite a bit quicker. But the point of doing the exercise is, let's say you had to do it a lot, or you wanted to string a whole bunch of calculations together. At that point, you might be better served by building a computational tool. So we'll go ahead and just enter those values. And let's go ahead and test some things. So we'll go ahead and compute the topographic slope using our slope function. And I'm going to make a guess of the flow depth under those conditions, except I'm not going to use one that's so correct, because that will work a little bit perfectly. Let me just kill off some of that stuff. Let's say I make an initial guess of 0.63. I'm a really good guesser, I might add. And once we know the depth, once we've specified it, computing the cross-sectional flow area is easily accomplished using our area function. Computing the hydraulic radius is easily accomplished using our radius function and our perimeter function. And computing the slope that's driving the process is actually easy enough. We can actually replace this right here, and we can kill that line. Bye-bye. And we can get a discharge associated with this depth. And what we would want to do in a practical sense is we want to make the discharge associated with our guess depth the same as the design discharge by changing the value of the guess. And kind of like using the goal seek in Excel. But here we're just going to do it kind of brute force. So in this case, our design discharge is 10, our guess was 9.96, and so that means we need to make our guess a little bit bigger. So we'll make it a little bit bigger. Now our depth is a little bit too big, and you can logically see what's going on here. And if we make enough guesses and we're pretty logical in our guessing step, we can conclude that the flow depth in this rectangular channel that's 5 units wide is 0.63 units deep. And that will produce the conditions that make our computed discharge and our design discharge the same. Well, that's not very practical as is. All we've really done is tested a thought process. And now we want to automate the process. And one of the ways I recommend automating would be to use Newton's method. Perhaps you've heard of Newton's method. It uses a confection from Nabisco that you can get in the store, and you put enough fig Newtons together, and before you know it, you have so much of a sugar high that you can solve these in no time. A quick review of Newton's method, if you call back from when dinosaurs roamed the earth and you perhaps first did mathematics. We can have some function, and we're trying to find what value of x makes the function equal to 0. And one way to do that is to make a guess, determine the tangent line, and project that tangent line back to the f of x equals 0 axis. And from that intersection, we do it again, we keep doing it, and we'll work our way over to the value that makes that happen. And skipping quite a bit of background, we ultimately come up with this formula that says that our new value of x is equal to our last value minus the function at the last value divided by the first derivative of the function at the last value. And then here's some examples using analytical derivatives. But we're going to use a method called a Quasi-Newton method. It's called Quasi-Newton because we're going to use finite difference approximations to approximate the derivatives. And the value of doing that is we don't always know what the function is going to look like. And in our case, our functions ultimately are going to get too complicated for us to conveniently find a derivative by analysis, but it's trivial for us, the human being, to find it using a difference quotient. And so the Quasi-Newton approach says that the new value of x is equal to the old value minus the function at the old value multiplied by some small value delta x divided by the function at the old value plus that small value of delta x minus the function at the old value. And that's called a Quasi-Newton method. And what we're going to do is we're going to steal that script, and I'm not going to mess with the input stuff, and we'll steal that script, and then we'll modify it for our particular instance. And so it's perfectly okay for me to steal from myself. And if you steal from me, just go ahead and cite the URL. So here I've done that. I've modified the function, and I have a function that goes by the rather cryptic name of func. And it has a single input value, which is whatever our current guess of depth is. I have to provide a way for the other values to get into the function. So I'm using this global designation. Again, we're not trying to make programmers out of you except for the scope of the next few weeks. When you use a global, be careful on what you do with the variables that are in the list, because if you change them, you're changing it everywhere. And that could that could be what you don't expect. I'm surprised this thing worked at all. I have a mistake right there. That and that are different names. Huh. Oh, that's cool. It somehow worked, or maybe it's not going to work. And then here's just the derivative function. That's absolutely no change from where we copied it from. This func does the following. If we provide a depth guess, it'll compute the discharge associated with that depth for the width values, the x1s, x2s, the Manning's N, and the design. And then it will take the design flow and the guess flow, subtract them from one another. It's trying to drive that difference to 0, and it'll return the current value of the function. So in other words, it'll tell us how close we are to 0. The next part is where we actually implement that Newton's algorithm. X new equals x old minus the function divided by its derivative. And then there's some output here. This is somewhat superfluous for ultimate use, but it's good for what we're doing right now. So let's go ahead and grab all that, or you could type it. And let me fix the errors that I'm aware of. that should be 3 n's, and need a way to get width into it. What else does it need? Width, everything else can pass through the argument list like it's supposed to. I'm surprised it actually worked. And then I've provided, it'll try nine times to refine the solution. That should be enough for this particular kind of problem. And then once a change is smaller than 10 to the minus 6, I'll declare that small enough and I can exit. And we'll start with initial guess of 0.5. We'll change that in the next modification. So what this does is it's going to attempt to do the same thing we've done up here, except it's going to be automated. And we want to test that, and that too is going to get wrapped into a functional process. So there's the algorithm. Here is something called a for loop structure. So it's going to pass through this thing from 0 up to how many times, and it's going to increment the counter I by a value of 1 every time. And that's a count controlled repetition. And then there's some tests that are implemented. If the new value and the old value are pretty much the same, we exit. Otherwise, we make an update and we return to the top of the loop and do the next pass. If the absolute value of the function is close to 0, we exit, and that breaks out of the loop. And otherwise, we do an update, increment the counter, and do it again. And then once the value of count is equal to how many, in other words, we've either exited the loop or we've hit the iteration count, we're going to go ahead and just print some stuff back to ourselves. And the thing we're interested in is this value x new, because x new is the depth at which QGuess and QDesign produce the same value, hence function is equal to 0. So interestingly enough, it gets there quite quickly, and I don't know what the iteration count is. So now we have that value of depth. If we were to go and put it up here, run that, sure enough, 10 equals 10. Yay us. Okay, so now we have an automated way to seek out depth in any channel, assuming that we know the geometry. Our next task will be to tidy things up a little bit, and we want to do a case of 3 nodes and 2 links. So now we're actually getting into our real modeling part. I'm going to copy and paste all this here, and I want to, there's a subtle difference. All the Newton's method has now been wrapped into its own function called getDepth, because again, I'm not creative. So here the only changes is I put getDepth. It takes one positional argument called xNow, which is our initial guess of depth. And when it gets done, it's going to return the value of whatever the final depth it could do in up to 9 iterations. Unfortunately, it's also going to print all this garbage because I didn't suppress that because I didn't want to break it just yet. And so now if I run that, let me make the repairs that I know I need. That has to have a third end, and we need to pass width. So apparently I actually don't have to pass global variables. It somehow knows what they are, but just from my olden days, I'm going to do that. So we run that, nothing happens. And that's because everything is now a function. let's check our get depth algorithm. So we know if we enter 0.5, it'll get to the correct value. And it does indeed get to the correct value. Let's see what happens if we're a really crappy guesser. That actually got there. That's kind of cool. This is not that well posed of a problem, so I'm surprised it's working so good. Especially since that's actually my own scripting. I didn't use built-in functions. Huh. Anyway, okay, well, cool. Yeah, it works good. I at this point, that right there is the result of it executing that statement, the returning value. And all this print stuff is just in the way, and we could suppress that in later versions. Now let's go back to our world, and we will start building our problem. Okay, so we're going to have a place where we have 3 nodes, nodes 0, 1, and 2. And node 0 is located at position 0, node 1 is located at position 100, node 2 is located at position 200. You can correctly think of those as distances downstream from some datum, in this case in meters. And then we can have the elevation associated with the 3 locations, 100, 99, it's supposed to be a 98, and 98. As of right now, there is no change in slope. Let's get it to work where everything's on the same slope first. And this particular structure is creating something called a list. So location is a list of things, 3 numbers. Elevation is a list of 3 numbers. And here we have a list that's empty called depth and a list that's empty called head. And the reason I have the empty list is I need to be able to put contents into it using a property called an append method, which is a property when you create a list. So this is a way to create space to put stuff in. For items that have multiple contents, you kind of have to create space for them if you're going to use those multiple contents and try to fill another item. Our next is our Manning's N and our design flow. So right now our world has essentially all the same properties up here, except the X1s and Z1s aren't described yet. So we've now created those objects. And since we've gone to the trouble to make a get depth function, we can solve information for the first reach. And by solving the first reach for our specified design flow, we want to find the flow depth between location 0 and location 100. And we have to pass the slope information. So we're going to set the value of Z1 equal to the contents of elevation, and then 0 is the pointer. So the first element is 0, the second one is 1, the third one is 2. We're going to set Z1 equal to that. Z2 is equal to the elevation associated with the second position in the elevation vector. X1 is the location with the first position in the location vector. X2 is the second position. So now Z1, Z2, X1, X2 are defined. Hence, they're now available to our function. And now we'll just use the get depth function. We'll make an initial guess of 0.5 because we have no other place to start. And to the depth variable, which is currently empty, we're going to append whatever result we get from get depth of 0.5. And the result we'll get is this 0.63. So we'll solve our first reach. When I run it, nothing interesting is going to happen. But because we had the internal printout, at least it gives some output. This is again helpful as you're making your initial development. Eventually, we're going to want to suppress all that because there's no value to having pages and pages of output unless you're getting paid by the character. And we'll now move to the second reach. Now, if we solve the second reach, we actually can immediately identify a pattern. We're just changing the subscripts on the elevations and locations, and then reusing the code. So if there were a bunch of different reaches, 10 or 12, we wouldn't want to do what I'm doing right here. We'd actually want to automate the process of changing the indices. But for now, we're just going to do it manually because we only have 2 reaches. We run that, and we get the same number out. That is intentional because where's our world? Currently, the slope is the same in the 2 parts. We only had 2 reaches, so the next thing we can do is we will compute the, I don't think I'm using the right word. This is the water surface elevation. And I'm playing a little trick here because if the slope of the channel changes from upstream or downstream at a node, by this method, we can't come up with a unique depth. But I'll just average the depths upstream and downstream of a node and use those, and then add it to whatever the node elevation is, and I will, for the time being, just declare that the water depth. The other trick I'm playing here is on the left end. Oh, damn it. What part of node? Why do you always interrupt? You're worse than a cat. How to make it go away? That worked. If I could seek out Bill Gates, I'd slap him for that. Although by now it's not his fault anymore. So on the left end, I'm just going to reuse the depth twice because there's nothing to the left of that. And on the right end, I'll reuse depth 1 twice because there's nothing to the right. And we'll see this trick again later on in the course. One can consider those locations as a type of boundary condition. And so we're just directly implementing a boundary condition at the left and right end. And the only intermediate value we have is at location 1, which is our second position, where there is a left and a right side, and that will do the formal averaging. So I'm now just using the append function. And our computations are done, but we need to go, let's go ahead and see what there is to see. So let's, we'll print out some results, and we have our looping structure again. So I'm going to create an object called iRow, again, because I have no creativity in naming. And it's going to go from 0, 1, and 2. And when it gets to 3, it stops. It never does the 3. So 0, 1, 2 is all iRow is going to take on values as. And I'm going to print the node name iRow, the elevation associated with that particular node, and the water surface elevation associated with that particular node, which I'm currently calling head. So I guess actually that is the hydraulic grade line. And so now I have at the leftmost The water depth has to be 100.63, at the intermediate 99.63, at the next one 98.63. Okay, cool. Woo, big whoop. That is indeed as simple as it is, and we'll go ahead and plot things.
Dr. Cleveland?
Yes, ma'am?
So the going back to where the text is, that print, does it matter if you put it on to Jupyter or no? Like the one before it. So go back to the lecture, like the lesson.
Yep.
And then right above the 4, I wrote that print. Yeah.
We put that there. That was just to make it look prettier.
Okay.
And all it's going to do is it's going to insert a blank line above these. So that's all it was doing. I guess the other thing would have been to print the new line character, but I get lazy because I don't like to do C programming in any way, shape, or form. Okay, so plotting may be something that you've not done, and I certainly am no expert at it. But all I did was go out to the mighty internet and ask the universe how to plot in Python, and then I've created this little script. So it's using an external package called matplot library, and I'm going to import something called pyplot from it as plot, and I have no idea what those do. I just copied this off the internet, but I put my own wrapper on it so that it'll plot list 1 versus list 2, list 3 versus list 4 on the same plot, and I can label the x-axis, the y-axis, and I can create a title. So and I currently have the markers turned off, so it won't actually show us the nodes yet, but we'll turn that on in a second. And I've made the bottom of the channel brown and the water surface blue, and I'm going to run that plot line where I'm going to plot location versus elevation and location versus head, and I'm calling the x-axis distance, the y-axis elevation, because I have no better name. And then the title is water surface profile. And with any luck, when this runs, we get that picture. Okay, so we just spent an awful lot of effort to plot 2 parallel lines that you can do with a hand calculator in a matter of minutes. But we could pattern match this, and it would not be a huge stretch of the imagination to have many links together. So I'm going to be a star. I'm going to choose the star symbol. And what this should do is it should put markers at 0, 100, and 200. The lines will still be there. There'll be dots at those locations. Okay, I want you to keep that picture in mind because we're now about to do the same thing in SWM. And in SWM, we will find, oh, do I have a local copy of SWM? Ah, sweet, I do. I don't have the most current one, but for what I want to accomplish, I do have one. So let's do that same thing in SWM. And so there is my SWM environment. Looks like everything's working. So I'm going to need 3 nodes. Yeah. I'm taking some shortcuts because I'm really familiar with SWM, sorry. I'm going to need to join those nodes to each other with links. So far this is, we think we're drawing, but we're actually writing code. We just don't know it. We need to turn that into a rectangular. The width was 5 units. We know it's going to be 0.6, but let's make it bigger. Sidewalls removed. Yeah. Its length is 100 units. We'll move on to the next one. We want to actually replicate that. So rectangular, height of 2, width of 5. Press the OK. Make it 100 units apart. Make it 100 units apart. Hopefully it. Okay, so I think we got that taken care of. I'm going to have to switch the flow units to CMS, cubic meters per second. So I guess that gets us into SI. And then our third most critter had an elevation of 98, 99, 100, 100, and I think I was using 0.02 in the computer example. And we need to put some inflow. All right, so that is what I consider the hard work of a SWM model. Actually, we need to change this from a free willy to normal. There we go. But now we have to decide what we're going to do. We're going to do routing. This other stuff is irrelevant, but we have to decide if we're going to do a steady flow or kinematic wave. We'll choose steady flow. That's all defaulted. That's defaulted. Dynamics turned off. So with any luck, this will actually run. And if we were to look at the SWM documentation, if we attempt it here, it just won't work. But if we look at the user manual, steady flow is trying to use Manning's equation. So let's give her a go. And wow, good. Flow routing was perfect. Let's check the flow. See if I remember how to do this. So it should give us 10 cubic meters per second, which is what we entered. Let's go to the junction and see what the flow depth is. It should be 0.63. Sure enough, it's looks like 0.63 to me, give or take a few 1,000ths. And now we'll go ahead and try to make the picture. In this case, I can use all the built-in properties. And sure enough, 2 parallel lines. This one gives us a third line for some other reasons. So we would now be obligated to convince ourselves that oh, Windows, how I hate thee. Let me count the ways. Although that was probably me, that was not the software. I still hate it. We would have to convince ourselves that that and that are the same. You can't really do it in pictures, but recall we did print the water surface elevation in a table, and we could do the same here in the SWMM tool. Let me see if I remember how to do that. I click on the table doodle by variable. I want, I think I want head, and I want it nodes. You switch a node and you plus it. Okay, so that should plot from node 1 to node 2 to node 3 from left to right, although I think I'll just do it in a list. And object category head, choose OK. And it says at node 1, the depth is 106.3, node 2, 99.63, node 3, 98.63. And when we compare that to our homebrew, we get essentially the same answers. So pretty much what we did by homebrew is what's going on inside the SWM software in the steady flow case. As the SWM software is a little bit more sophisticated, especially when slopes are changing. So let's go ahead and try that in our homebrew, and then we'll go back and look at it in SWM. So what I mean by slopes are changing, let's look at the case where instead of that being a 98, we'll make it a 96. So the slope there is going to go from 1 part in 100 to 3 parts in 100. Steeper slope. So we change our world. We solve the first reach, no change there because we haven't changed anything geometrically. Look at the second reach, and now our flow depth is less because it's steeper, so there's more gravitational driving force. We'll go ahead, recompute our heads. So now we're 163, 99, 53, 96, 44. We'll make our plot. Well, actually, that came out pretty cool looking. So there's our plot. We've now plotted 2 lines. Let's repeat that in SWM. See, I want to leave that up because I think it can update. So now that instead of going to 98, we go to 96. Rerun everything, press the okie dokie. And here's the interesting case that I was trying to describe, in that the flow depth to the left of the node is deeper than to the right of the node because there's a slope change. Let's see what the SWM programmers did. 163, 99, 63, 96, 44. I used averaging. They do something different. So I have 100.63. I have 99.53. So I'm averaging that depth and that depth. And 96.44, 96.44, we agree when we get to the end. So the only difference now between SWM and our homebrew is how we're handling the situation where the flow depths change moving from one side to another of a junction. Oh, you all missed that. I just got a cat in my face. Oh, you get to see his shadow in the, well, hello. You gonna teach class, or are you telling me it's time to wrap it up? Okay, so anyway, the main difference is how we handle these things at the nodes, and I would have to read the SWM technical manual to see what they did, but it looks like, judging from the picture, that they actually follow something called a directed graph, the mathematical thing. And so the depth of the node is always whatever the upstream depth is, and then it starts plotting on the next one. And that's a reasonable approach. That's as good as any. I chose to use averaging because I didn't want to encode the computational logic to do that. So I stipulate that at this point, for all practical purposes, we've replicated the computation engine of SWM to some extent. We'd be a fool to use our homebrew one instead of SWM, because the homebrew one is clearly, I'm wrestling a cat right now. Give me a second. The homebrew one is clearly a little hard to build inputs for. We actually have to define our world every time. And what the SWM interface does is it lets us draw our world. All right, 9:12. There's 8 minutes to go. I think I will stop here. I will allude to where we're going next time. So what we're going to do next time is we're going to look at gradually varied flow using variable spatial steps, and we'll go through the same procedure again as a workshop kind of thing on how to build these. This time we'll do it again in SI units, and I'll save the conversion to US customary for a homework assignment, which is coming up next week sometime. And again, get everything working, and then I put them into script wrappers. And that is, I think for the few that you're going to have to do for this class, you'll find that convenient, because it helps you keep, once you get something working, throw it into a function so you don't have a chance to break it. All right, this is a good time to stop, and I will let you see the cat. Say hi to the internet. Hi, internet. This is a very elderly cat, so he demands attention at completely unpredictable times. All right, well, that's all I have for tonight, because if we go on, I think it will confuse the issue. I have a couple questions for y'all before we quit. Was that slow enough that you'll be able to, you don't have to necessarily keep up with it live, but you should be able to watch the video plus whatever notes that you've taken and be able to replicate that information. So that was a question. Was that slow enough?
Yeah, I think that was good. It was,
Okay.
it was easy to follow.
Good.
So that was
Yeah.
adequate speed?
Yes.
Yes,
Good.
I agree.
All right, well then I will, that's good to know. So I will probably use that cut and paste, because that slows me down. And since I don't like to type, you don't have to worry about me typing stuff real fast. And if you actually want to get this HTML file is actually created using this notebook right there. So your other option is to see if I can, mouse is just not working. Cat, did you eat them? Oh, are you sitting on the keyboard? Yes, you are. You're fine. Just don't step on stuff. You can download that file and then operate on it directly. I will attempt to demonstrate. Why don't you sit right there? I'll be done in a few minutes, okay? You had all day to bug me, and you waited till now. Okay, I don't want Teams. I want to... Oh, that's the wrong one. I'm gonna go to that one. I'm going to demonstrate that you could just download. Don't look at the names of the lessons, because that's all not right. And trying to get it to the right directory. So there's the notebook I just downloaded, and you can run it. It's all there. So that don't get dependent on that from me, but at least for these first few. So there's what I mean by the pink screen of error, and it's telling me Q norm is not defined. Rather than worrying about it, what it really means is I actually need to run the entire notebook. And now it's defined. So now everything runs. And wonder when I change the oh, there it is. That's weird. I don't remember changing it in the lesson. And again, we'll go through the second part next class meeting. Okay, so good evening, everybody. Have a great let's say have a good afternoon, but that doesn't make sense. Makes sense for Jawad, who I think had to disconnect. Hopefully, well, he'll be able to watch the video. And I will see you on Thursday, and we'll continue with some more of this.
Thank you,
I'll
Dr.
see you
Cleveland.
Wednesday.
All right. You'll see me Wednesday. Oh, that's right. There's now the cat is completely in the way. Anyway, good night, everyone.
Good night.
Night.